In the previous segment, we were talking about the different cases of axial loading, and under that we saw the first basically type of problems where we talked about multiple loads when they are acting on a single rod, and as we had discussed in the previous segment, so the next topic which we will take up is that of continuous loading. Okay, so what it means is, see, suppose you have a rod which is hanging in a uniform gravity. Okay, now in this case, if you observe, what happens is at any cross section, if you look at that cross section, the weight below that is only acting, right? So if you consider section A, so this portion of the rod is trying to pull it down. Now if you go to say cross section B, now then all this volume of the material, so they are pulling it down. So what it means is, at every location X, the force which is trying to pull down is different. So that means this is the case where the force is varying continuously. Okay, so it's not a constant force, it is not a concentrated force acting at a point, and then so like in the previous case which we saw. Okay, so in this case it is changing at every location. Similarly, another case is that of say a rod which is changing in area. Okay, and you are applying the same force, let's say here F and F, but the area is changing every location. Now so again, so its area is changing. Now the third case could be that of say the rod is same, maybe even the force is same. Okay, say a force F and another force F is acting, but you are using a material which is changing its property, maybe the Young's modulus which you are using, so that is different, or that okay, say so here maybe the Young's modulus is more, and as you go in this side, so maybe the Young's modulus is less. So E is a function of X, where X is in this direction. So either this condition, or this condition is present in the problem, or combination of any of them. Okay, so then the problem becomes little bit hard, because you remember what we did in the multiple force applying condition. So we split the domain according to wherever either the area or the force or the material was changing. So based on these three types of discontinuities, you were splitting the domain, and then each of those domains were behaving like your canonical problems. But now here there is no such instantaneous or immediate discontinuity, because everything is continuously changing. There is no, it's not a step increase of area, so that you can't now segmentize the way you did here in the previous case. So in this case, the idea is then to take at a location say X from here, you have to consider a small enough length dx. Okay, over that you can consider the area to be constant. In this case, maybe you will think that Okay, yeah. So this area is considered to be constant here. Okay, it's not changing, and that area will be the area at that location x, and then it's like a condition where a constant area and there is a force here and there is a force here, and then this length is dx, so this becomes your canonical problem, and you know all the formulas which can be applied for such a problem. Exactly in this case also, in this case at a distance x, you can consider the f to be a constant across that. Suppose at x distance you take again, you know, a length of dx. Okay, now over that say segment of dx, you will again, or so I'll just say that the force which is acting is constant. Okay, and area is the same, so it doesn't matter in this problem. So again it goes back to the canonical problem, and in this case you will consider, say suppose here over this dx, you will consider E, which happens to be the E at that particular location, and that you should consider to be constant. So that is the whole story of having what do you call, I mean, how to solve these kind of problems. Okay, now so if I want to, yeah, I'll write here only somewhere. So in this case, suppose the area is changing, what you can do is for this case I'm writing, for example, small d of delta. If the elongation is delta, the total elongation of the rod is delta, so the small change which happens due to this portion will be, you know, your force over area at that particular location, which is a function of x. Okay, and then so this is the stress. So this once you divide by E, it becomes say so what I will do is I'll combine all the variations. So F could be varying, A could be varying, E could be varying with x. Okay, now this becomes stress over E, your strain, times your dx. Okay, so this is your small increment in your elongation because of this small segment which you have chosen, and then you can just get the delta by integrating this delta, which is the integration of f of x over a of x e of x dx. So that's the whole thing. So if you go to a particular problem like this, so in this case fx is changing, all other a are constant. In this case a is a function of x, but f and e are constant. In this case f and a are constant, but e is varying. So but there could be a problem where all the things are changing. So that's how you should be able to solve the problems. So I just want to make one point here. You remember we were discussing about a problem like, say there is a rod like this, and suppose you are applying a force here F and say F. So that was our canonical problem. Now suppose these two forces are not equal. Suppose this is F1 and this is F2, and assume that F1 is greater than F2. Then what will happen? So what will happen is because they are not equal, because of the difference, it will create an acceleration depending on this mass of this rod. Okay, because suppose F2, so this F2 portion of F1 will be responsible for creating some stress, okay, which is like a static stress. Okay, in this case I am assuming F2 is small, so out of F1 whatever is that F2, so that much portion will be trying to elongate this, so that is one part. But then there is the other part, which is F1 minus F2 portion, that will try to move this rod in an accelerated way. Now you know that in an acceleration is equivalent to, like, you know, a gravity in the other direction, if you consider the pseudo force sort of. Okay, so for small the constant accelerations are like equivalent to constant gravity field locally. Okay, so that can be used so to convert this problem into such a problem where this G should be replaced with the A, which is nothing but F1 minus F2 over m. Okay, so now this is the acceleration is happening in this direction. Okay, so then the pseudo force will be acting in this direction, and along with that, say one F2 is acting here. Okay, so in a way, so this roof is providing the other F2 part, and then this acceleration or the gravity field is taking care of this F1 minus F2 over m, the acceleration, so that will take care of this varying field. So this will have two components, one because of this constant F2, and the other one is this varying force which exists across the length. So that is how you should be able to solve the problems. One more case where this kind of varying force will come is, suppose you have a rod, for example this ruler. So there is a hole here, right? You are seeing that. Now this one, suppose I put something here and I rotate it. Okay, about this point of this ruler. Then from the center, suppose it is rotating about this point. So from center, if you go to different distances, you will have different accelerations. Again, the same acceleration can be considered as the gravity which is existing at that particular location. Now in this case, it's not a case of constant gravity, but it's a case of, say, varying gravity you can think of. Okay, even the G is not a constant, but G is changing with the distance r from this point. So these are some of the basic problems which you can always solve. So I wanted to just make clear about that. So what type of problems are generally coming under this varying force, continuously varying forces area of material. In fact, one more point I want to make here, that though we are studying these things in the axial loading case, mostly they are of academic interest. Practically hardly you will find such problems. Yeah, but you will find actually, but not much. But once we go to the next topics, like the bending, I was telling you, right? So axial loading, torsion means pulling, pushing, twisting, then bending. Now as soon as we go to bending, almost all the problem will be of continuous loading type. Okay, so that we will see, and then whatever we are discussing here will be very, very useful conceptually to understand such problems. And in fact, we will have in those cases we will have methods to represent these continuously varying forces, varying moments, and all those things. We will have diagrams to represent them, which will be called shear force bending moment diagram. We will come to them. Okay, just yeah. And something else I wanted to say. No, I think that, yeah, that's fine. Okay, so that's it for discussion about the continuously varying load. In the next segment, we will be talking about the other genre of problem, which is the restrained one. That means the statical indeterminate cases. Okay, so see you in the next segment.